Does anybody know what time the library is open till during the week?
Probably like 9 o'clock.
Okay, so it is like later.
I think it was 9.
All right. A few more to go. There we go. All right. How was my weekend? Good. I saw Riverdance up in Boston. Yep. I didn't think I'd like it as much as I did like it. Music's really good. The dancing's. I am not Irish. Not even attempt to. I am Polish, but I don't really get into any of the traditions. Uh, the Polish birthday song? Is it the same as the English version? I just learned something new. Are you? Yeah, the rave music over there is a lot better. I don't know about Poland, but I know like Switzerland and Netherlands, and those are all the good DJs are. Anyhow, yes, I had a good weekend. What do we have for left time frame wise? Not much. So this week, next Wednesday, I got to correct. Not Thursday, not Tuesday. Wednesday the 23rd is our exam number 4 and then a week after that is our final exam. So yeah, not much. And just to give you a heads up, so today we'll talk about, well, I'll tell you, it's called logarithms, but scary word for something that's not scary. But that's really the main goal tonight. Probably a little carryover into the 16th, and then on the 16th and next Monday, our last topic called rational functions. Anyhow, that's that. And then exam, review, final. So counting them down. Still can book tutoring. I'm available after class on Wednesdays. And in terms of final review, I'm really putting my effort in this week since I'm off from school, Cranston Public School. So I'll be hopefully have that for you the next time we meet. If not, I'll probably post it at some point by the weekend so you can really focus in on your skills. But if you're still looking to do something before then, as I've been saying, review your previous exams. That's what I'm looking at predominantly.
You said 4 exams in 23rd, right?
Yes. Yep. All right. So as I said, tonight's main goal is to talk about logarithms. But before we do that, I saw this from a different mathematician. I think I've referenced him a few times, it's James Stanton, as an intro to logarithms. So before we do logarithm, see if you can figure out what I've written so far. And this is intentional. I'm not saying something like, might you understand what I'm trying to convey when I write the following 3 equations? And a good test to see if you do have it is if I said something like, how about this? Any ideas? Any ideas? 2. Why do you say 2? Because 3 squared is 9. 3 squared is 9. Okay. And so how does this statement come from here? How did you kind of reason through that based on the previous examples?
Well, I had previous knowledge of this.
Previous knowledge of this. Okay.
And the answer is right after the power up on the bottom of the block.
Oh, so there's a word, power. Okay. Power. So correct. I've shortened the word power to pow.
So it's just stating like what, how many powers of 2 get to 8? Like 2 to the 3rd power would be 8. 5 to the 2nd power would be 25.
So you're seeing it now as 3 is the number of powers, or we could say like the exponent on 2, that makes 8. So let's kind of confirm this cleanly. So 2, I'll make this a red 3. And 2 to the 3rd power, or as you said, the number of powers on 2 that make 8. Let's see, 2 times 2 is 4 times 2 again would make 8. So yeah, that works out. Is that kind of hold all the way down? 5 to the 2nd power does indeed make 25. And lastly, 4 to the negative 2 power. Exponent properties back definitely tonight. Negative exponents are like positive exponents, then flip the answer. So 4 squared is 16, and then if you flip that answer, you would get, did I just say 14? 4 squared is 16, and then flip that answer would be 1/16, which we see right there. And so lastly, question mark on base 3. Yeah, I think the question mark has to be 2. Actually, I know it has to be 2. This should be that, and we'll keep that here. Hey, everyone see it now? Yeah. Neat. So actually, we're done for tonight. No, I'm kidding. But you've just done logarithms. That's all logarithms are. Fancy word. I wish I could call them POWs, P-O-Ws, not prisoners of war, but POW, and it would be a lot less scary. So we are not talking about what power functions. We are talking about logarithms. And a logarithm is an exponent. Or a power. That's it. Historically, the reason we don't call it powers is historically the time frame when they were discovered, the word for power or the mathematician didn't use the word power. So this scary word logarithm has stuck around. But that's all a logarithm is. It's an exponent at the end of the day. So we abbreviate logarithms as log. And very similarly, we would write that. We say the base 2 logarithm of 8 is 3. That's how we read that sentence formally. Although if you said like log 2, 8, it can be kind of confusing. So I'll do my best to read it formally, but sometimes I say like log base 2 of 8 instead of the base 2 logarithm. But I know that's like the formal way of saying that. And we can immediately convert a logarithm expression to an exponential expression. So I want to emphasize that this right here is your base. And this right here is your exponent. As I said, when we have a logarithm, what's on the other side of the equation is an exponent. Logarithms are exponents. So if this is saying logarithm, then it has to balance with an exponent. And this is the base. So base 2 to the power of 3 equals 8. And this is called your exponential form. Literally one test question and probably a final exam question and many homework questions will ask you to convert a sentence that's given as a logarithm into its exponential form and vice versa, starting with an exponential, convert it to its log form.
So is the exponential
this right here.
Oh, okay.
And this right here is called your log form. So, for example, the base 2 logarithm of 64 is 6. So that's what you'll be given. A little study tip. I learned this from one of my teacher friends. When she teaches it, she just tells her students, you keep the 2 as your base. The 6 becomes your exponent. And the 64 is like your answer. That's it. And this is what you would input in MyLab, this entire sentence. We don't always just use numbers. We can do this with some algebra involved. The base 9 logarithm of x is 2. Keep your base. Interchange here. And there we go. Now, if you're wondering, well, can I simplify that? Yes, you can. But in your homework, I double checked this just to kind of emphasize converting forms. Don't call that 81. There's 3 parts kind of to a logarithm: the base, the exponent. I guess we'll call this like the answer. And so here's your base, here's your exponent, there's your answer. Write in log form. So keep your base. And swap those kind of numbers. So the base 5 logarithm of -3 is 1/25. Wait, nope. I didn't swap anything, did I? I was going to say, wait a minute. There we go. The base 5 logarithm of 1/25 is -3. There we go. Put your arrows in, but make sure you change it. And again, just something you might see with variables, and then we'll do something a little bit interesting. Finding the see if I can get it right this time. There we go. It's pretty straightforward, just kind of knowing that's all a logarithm is. It has an equivalent exponential form and vice versa. An exponential has an equivalent logarithmic form. So put a little star here. Maybe a couple stars here. How do we convert this guy to a logarithmic form? So you're definitely going to see this in the homework and potentially exams because it's used. It's not just meant to be challenging. When you see roots, associate them with powers. I think I've said it when we went through that lesson weeks ago. Feels like weeks ago now. But definitely in calculus, big thing. Roots are easier as powers. And the same is true right here. So before we convert this, the first thing we're going to say is 64 to the 1/3 power is 4. So kind of making a substitution. Cube roots, 1/3 power. And as a reminder, square roots are 1/2 powers, and 7th roots would be 1/7 powers. All those things are true. From here, it's just a matter of now saying, keep your base, change the position of those guys, and you're done. Right? And that's it in a nutshell. For starters, that's what a logarithm is. They're kind of like what power, that's how you say them in your head, what power would give this number. Let's see, there's a bunch of these. I'm just going to list out a few. Might have already done some of these, just gonna. Scared yet? So to give you some insight in my brain, it's literally what I showed you at the start, how I opened this lesson. This still intimidates me until I say, bro, this is just a what power. What power? How many powers on 4 makes 16? When I train my brain to read it that way, it becomes a heck of a lot less scary. So what power of 4 makes 16? 2. What power of 3 makes 27? 3. Okay. Little more thinking involved. What power of 5 makes a 5th? -1. 5 to the first is 5. I want to flip that answer. Oh, so it's not to a 1 power, it's to a -1 power. What power of 3 makes a 9th? -2. I'm going to pause, even if you're already thinking ahead. I could replace each of these. That 4. Don't worry about your notes. I'm sorry, that 16 as 4 to the 2nd. And I can replace this 27 with 3 cubed. And this 1/5 as 5 to the -1. And this 1/9 as 3 to the -2. And if I made those substitutions, I want to show you what I'm throwing at you. It's like the base 4 with this base 4 cancel out. This base 3 and this base 3 cancel out. This base 5 with this base 5 cancel out, and this base 3 and this base cancel out, and the exponent literally becomes your answer. So, if you liked what I did there, carry on. If you don't like what I did there, carry on. I'll give you guys a couple minutes just to kind of think about some of these on your own for a moment. I'll go 30 more seconds, even if I didn't get to all of them. Just giving you an opportunity to think. All right, so the base 7 logarithm of square root of 7. 1/2. And so if it helps to rewrite it, go for it. Or if your brain can rewrite it, that's how my brain works. I like what I showed you in like the rewriting steps for when things get complicated. So I'm like, all right, square root of 7, need to call that a 1/2. And then the base 7 logarithm and literally the base 7 cancel out. And there's your answer, 1/2. And with practice, although when do you really practice this if you're not in a math class? Probably never. It's not like anyone's going down the street doing this. But with practice, say this is really 5 to a 1/3 power, the base 5 and the base 5 cancel out. You'd have a 1/3. What power of 6 makes 6? 1. What power of 11 makes 11? There we go. That sounds like a property, which we're going to get to next. Actually, what power of a base gives you that base? What power of 6 gives 6? What power of 11 gives 11? What power of b gives b? 1. Yeah, let's get to it. So I'm jumping ahead, but that's what I was going to next. We're going to call these basic properties. There'll be a couple. Bless you. What power of a 4th makes 4? -1. And what power of an 8th makes 8? Bless you again. And what power of 5 makes the number 1? Hey, there we go. Onwards. Okay. So before I get to the basic properties, even though I kind of had to write that one right there because it was just screaming. Without a calculator, as I said, just some basic ones. So knowing like powers of 1, 2, and 3, it's pretty much all you need. In addition, remembering that negative exponents kind of flip things. So if you have, for instance, this was a 1/9, but a base 3, that should be kind of vibing negative exponent in my answer. Similarly, over here, you have a 1/4, but you're getting a whole number 4, kind of setting you forward in your future coursework with just kind of thinking negative answers there. All right, onwards, basic properties. So the base b logarithm of b is 1. Another property that we saw. We saw this? Yeah. Logarithm base b. And here's a base b. What's my answer? Yeah, those cancel out. That was this guy right here. But I don't want the blue in your notes, right? So I'll do it again so you can see. That's what we've shown. This and this cancel out. That is a property we want to use. The base b logarithm of 1, no matter what the base is, we're going to say 0. There we go. And those are our first 3 basic properties. I don't memorize them. I really don't, but I have to go over them. The next set of properties, I'm going to tell you, need to memorize. But these, they're there. I just talk them out. What power of b gives b? 1. What power of a base gives the number 1? So I'm just thinking powers. I need to make 1 as an answer, 0. This is the interesting one, but showed you. But it's basically saying, as I've said in words, but so you have in your notes, log base b cancels out base b. And we'll need that when we look at equations, just some easy equations. This is what's going to allow us to solve equations shortly. But the other two, pretty straightforward. Okay.
Is there a basic property for the square roots?
Just knowing that if you see a root, write it as a 1 over the n power, but no, not formally. But we can make one up. Anyway, I think we just did. If you see any type of root, write it as an exponent first. Okay, graphing logarithms. So my strategy, obviously, that I'm sharing with you is right here. I like to take a logarithm and rewrite it in its exponential form. Keep the 2 and the y and the x are going to interchange. I'm going to give this a little more color coding. So 2 to the y is x. Bless you. The next thing I do is also a little different. I don't start. It's like one of the few times in math I don't sub in numbers for x. I sub in numbers for y and figure out the x. Because it's easier for me. I know some facts pretty quickly about 2 to the negative 3, 2 to the negative 2, 2 to the negative 1, the 0, the 1, the 2, the 3. And maybe this will be enough. This is more than enough. So when I say you do enough values, I think, well, I know this will be enough for us. But here's where I am. Rewrite it, and then paying attention to, it's easy for me to, one, go to Desmos and just see what the graph is, but without a graphing calculator, just kind of think about 2 raised to different powers. So 2 to the negative 3 is 1/8. 2 to the negative 2 is a 1/4. 2 to the negative 1 is a 1/2. 2 to the 0 is 1. 2 to the first is 2. 2 squared is 4, and 2 cubed is 8. And just a few lessons ago, this table of values was changed. These were our inputs and those were our outputs. So I'll come back to this in just a few minutes, but this should seem eerily familiar, just not identical to what we're recently doing. But these were in the X column and these were in the Y column, and we had something called like exponential growth. Yeah, this right here is exponential growth. It's something that has an asymptote and then skyrockets upwards. And hopefully you saw the lesson. I did put the due date for this Thursday just because it was something I wanted to do for the compounding interest. But if you haven't got that done, the official full credit deadline is, why I say Thursday, this Wednesday. Then it enters late credit. So if you haven't done that homework, make sure, hopefully you get that done by Wednesday for full credit. But this is an exponential curve. Well, it's not X equals Y, but like not 2 to the X equals Y. But if it was, that would be an exponential curve. Very, very similar. Now when I graph these, just plot some points. 1/8. Starting at the origin, break this up into 8 equal parts and go one of them. So my point there is, bro, you're really, really close to the origin. Really, really close. -3 would be like down here somewhere. One-fourth. Imagine this segment broken up into 4 equal pieces and go the first segment. And you output -2. So about right there. 1/2, -1, right smack in the middle. 1, 0, 2, 4. I'm sorry, that's false. 2, 1, and then 4, 2. Let me just put the curve in, and then we'll digest it. And I should have hit that point, so I'm gonna lie a little bit. There, hit it. And there's your graph of, I guess, 2 to the y equals x. That is literally the graph there. But actually, it's our original function too. Y equals the base 2 logarithm of x. And so just a few minutes ago, I was talking about how this is very recent in our knowledge in this course. It kind of feels exponential. When I stand right here, I'm kind of seeing an exponential curve if I like use my perspective in this direction. Although it's not quite growth, but right, here's something that it's like if I'm not looking at it this way, when I look at it this way, I see what I see. But if I could look at it this way, if I was standing in that orientation, I'd be like, oh, that almost looks like exponential decay. If this was the x-axis, like we just switched it, kind of get what I'm throwing at you? Yeah. Cool. And that was intentional. I wanted to kind of associate this data table as something that's super close to being exponential. Because here are some key features of logarithmic graphs. Exponential graphs had y equals 0 as long as there was no transformation as their horizontal asymptote. Well, change your perspective. There's an asymptote, but it's not horizontal. When I look at it as a human, we get a vertical asymptote. The vertical line x equals 0 is a vertical asymptote. And that emerges from what I was trying to sell over here earlier when I was saying 1/8 is just a smudge past the origin. We're really, really close to the origin. If I did more data points, like -4, that would have been 1/16. Even closer to the origin. Never mind something like -10, that would be 1/1024. Break that up into 1024 equal-sized pieces. That's ridiculously small. So you're getting closer and closer and closer to the y-axis. And that would be your vertical asymptote. Okay. Looking at this, is it possible that we're going to get negative numbers? And the answer is no, we're never going to input a negative number. Why not? Well, because the way I built this table, I can continue to think about as many negative y values as I want, but that's never going to pair with a negative x value. Bigger y's make bigger x values. Negative y's make positive fractions. They make small, small numbers, but not negative. So we're never going to get a graph over here. Therefore, our domain is 0 to infinity. But looking at the range here, we do have negatives, we do have zeros, we do have ones. And so our range is all real numbers. So in just a second, I'm going to put this on paper, but this was a very specific example. This was a base 2 logarithm graph. If this was a base 3 logarithm graph, I would rewrite it in its exponential form. I would choose the same numbers in the y column. It would change the values over here, but here's what would not change. For instance, let's just talk it out. This was base 3. 3 to a -3 is 1/27th. 3 to the -2 is a 9th. 3 to the -1 is a 3rd. You still get positive fractions. 3 to the 0 would be 1. And 3 to bigger numbers just make bigger numbers. So if you caught what I'm trying to sell to you, it wouldn't be exactly the same graph. It'd have slightly different numbers, but its shape would be the same. And that's true if this was 3, 4, 5, 6, 7, and so on, and so on, and so on. What if we had a fractional base? Would that be the same as like a base 2 graph, a base 3 graph, a base 4? Well, one way to figure it out. Let's do it. Rewrite it in its exponential form. Easier to think about exponents than logarithms, because that's what they are. Just make sure you put your values for y in the right position, in the y position. 1/2 to the, let's start with the easier ones. 1/2 raised to the 3rd power is an 8. Therefore, 1/2 to the -3 power is 8. 1/2 squared is a 4th. So therefore, to the -2 would be 4. 1/2 to the 1st is a 1/2. To the -1 would be 2. And to the 0 power is 1. And I'm already visualizing this is not going to be the same type of shape as our other graph. Let's see. One-eighth, way down here. That's just past the origin. I need to output the number 3. One-fourth, about right there, has to output the number 2. 1/2 has to output the number 1. Not quite a half, I can do a little better. And 1 has to output 0. 2 outputs -1. 4 outputs -2. Nah, not the same shape. Definitely have some vibes that are the same. One of which is we still have a vertical asymptote at x equals 0. We still have a domain that's 0 to infinity and a range of all real numbers. And I'll come back to this in a minute, but just so I can say it out loud. The biggest difference is we say this graph, as you move to the right, is increasing. It's going up. If you're a stick figure, if you're a ladybug, and you move to the right, you'd be climbing up a hill. Whereas this graph, if you're a ladybug, an ant, you were moving towards the right, you'd be going downhill. You'd be coming down. I'll summarize that in words in just a second. I know some of you are finishing up here. And those are our takeaways from the graphs of logarithms. whether you have a base